Welcome to Particle Physics Podcast. In this special episode, we are heading to CERN, the world's leading particle physics laboratory, to explore how scientists use giant accelerators like the Large Hadron Collider to recreate tiny moments from the early universe. We'll unpack what CERN actually does, why smashing particles helps us understand reality, and how the discovery of Higgs boson changed modern physics. Stick around as we dive into the machines, the mysteries, and the breakthroughs shaping the next era of fundamental science. What CERN does is easier to summarize than to truly imagine. It recreates conditions similar to those that existed fractions of a second after the Big Bang, then measures what happens with exquisite precision. The core strategy is simple in concept: accelerate particles to very high energies, collide them, and study the spray of new particles produced. But the execution is where CERN becomes almost science fiction. It builds and operates purpose-built particle accelerators, machines that push beams of particles to near light speed, and detectors, giant cameras that record the outcomes of collisions. The most famous accelerator is the Large Hadron Collider, LHC, a 27-kilometer circumference ring underground in which two beams circulate in opposite directions and collide at several points. Around those collision points sit experiments like ATLAS and CMS, general-purpose detectors designed to capture as broad a range of physics as possible, along with specialized experiments such as LHCb, focused on heavy flavor physics and matter-antimatter asymmetries, and ALICE, focused on heavy ion collisions and the Quark-Gluon plasma. The collide and record approach is only half the story. CERN also has a whole accelerator chain feeding the LHC, plus facilities that produce and study rare isotopes, antimatter, and other forms of beams. Under the hood, the LHC is not just a ring, but a symphony of technologies: superconducting magnets, cryogenics, ultra-high vacuum systems, precision timing, and control software, whose performance is as much about reliability and reproducibility as about raw energy. And because every meaningful collision is a tiny statistical miracle, CERN's experiments are built around the idea of filtering the interesting from the mundane. Sophisticated triggers and reconstruction software decide, in real time, what to keep from a flood of events so large that saving everything is physically impossible. The Higgs boson discovery is the moment when all of this, history, infrastructure, collaboration, and physics, clicked into a story the whole world could understand. In the standard model of particle physics, the Higgs field is the mechanism that allows elementary particles to have mass without breaking the mathematical consistency of the theory. The Higgs boson is the quantum ripple of that field, and finding it was the missing keystone that would either complete the model or force a radical rethink. The LHC was built, in significant part, to explore the energy scale where the Higgs was expected to appear and to test the standard model at unprecedented energies. After the LHC began producing high-energy collisions and the experiments matured their analyses, two independent collaborations, ATLAS and CMS, started seeing a consistent excess of events in multiple decay channels that looked like a new particle with Higgs-like properties. On July 4, 2012, CERN held a packed seminar where the spokespersons of CMS and ATLAS presented the evidence: a new boson near 125 giga-electron volts with statistical significance strong enough to qualify as a discovery. That day mattered not only because a particle had been found, but because it validated a half-century of theoretical structure and demonstrated a modern mode of discovery: two massive detectors with different designs, two separate teams, converging on the same result using different methods. Since then, the Higgs has shifted from missing particle to precision tool. Its mass, production rates, and decay patterns are now measured to test whether the Higgs behaves exactly as the standard model predicts, or whether tiny deviations hint at deeper physics. In that sense, the Higgs discovery wasn't an ending. It was the opening of a new experimental program where the goal is to interrogate the Higgs with enough accuracy that it becomes a microscope for new phenomena we can't produce directly.
That broader physics potential, what CERN is really for, beyond any single headline, spans both the known and the unknown. On the known side, CERN provides the most stringent laboratory tests of quantum field theory ever performed. Quantum chromodynamics, QCD, in extreme regimes, electroweak physics at high precision, and the internal consistency of the standard model across many observables. On the unknown side, it targets the questions that keep particle physicists awake. What is dark matter? Why is there more matter than antimatter? Are there new symmetries in nature, supersymmetry, compositeness, extra dimensions, that reveal themselves at higher energies or through rare processes? Why are neutrino masses so small, and do they point to physics at scales far beyond our direct reach? The LHC program attacks these mysteries in two complementary ways. First, it performs direct searches, looking for new particles produced in collisions, heavy resonances, long-lived particles, exotic decays, missing energy signatures, basically trying to catch new physics red-handed. Second, it performs indirect searches through precision, measuring standard model processes so accurately that any deviation becomes evidence of new forces or particles influencing the results from behind the curtain. Heavy ion collisions, meanwhile, let CERN study QCD matter at temperatures and densities where quarks and gluons are not confined inside protons and neutrons, giving insight into the early universe's primordial plasma and the emergent behavior of strongly interacting matter. And beyond the colliders, CERN's ecosystem includes experiments that probe antimatter properties, rare decays, and nuclear structure, programs that look different on the surface but share the same philosophy. If you want new fundamental insights, you either go to higher energies, higher intensities, or higher precision, and ideally, you do all three. Looking forward, CERN's next chapter is about scaling up both the quantity and the quality of what it can learn from the LHC, while also exploring what comes after it. The High Luminosity LHC, High Lumi LHC upgrade is designed to massively increase the number of collisions delivered over time, turning rare processes from maybe we'll see a few into we can study this like a real dataset. CERN describes High Lumi LHC as capable of collecting up to 4,000 inverse femtobarns over its operational period, and producing more than 250 inverse femtobarns per year, an avalanche of data that will sharpen Higgs measurements, expand sensitivity to new physics, and enable detailed studies of extremely rare standard model processes. Schedules for big machines move as reality asserts itself, and CERN has noted that an updated accelerator schedule shifts the start of the high luminosity era, Run 4, to around June 2030. Parallel to that, CERN is actively studying longer-term options like the Future Circular Collider, FCC, with a tentative timeline that includes the release of a feasibility study report in 2025 and a member state decision around 2028, followed by construction in the early 2030s and later operations in subsequent decades. And it's worth underlining that CERN's impact isn't confined to physics results. The lab has repeatedly had outsized influence on technology and society, most famously when Tim Berners-Lee wrote the first proposal for what became the World Wide Web at CERN in 1989 to help scientists share information more easily. So if you zoom out, CERN is best understood as an engine that turns deep curiosity into durable infrastructure, machines, methods, and communities that keep expanding what humanity can measure, compute, and imagine. Looking beyond the high luminosity LHC era, CERN's main long-term next flagship concept is the Future Circular Collider, FCC. a proposed new underground ring of roughly 100 kilometers around the Geneva region, larger than the LHC's 27 kilometers, designed to be built and operated in stages, typically described as an initial electron-positron collider, FCC-EE, for ultra-precise studies of the Z, W, Higgs, and top, Higgs/EW/top factory, followed later by a proton-proton collider, FCC-HH, aiming for about 100 TeV collision energy to push the direct discovery frontier far beyond today's reach. CERN released the FCC feasibility study report in 2025, explicitly framing it as a basis for evaluation rather than a commitment to build. It then went through reviews and council discussion, including a dedicated council meeting in November 2025 as part of the wider European Strategy for Particle Physics update process, with council-level milestones continuing through 2026 and an often-cited decision window around 2028 on whether to proceed. The physics promise is huge. Precision Higgs measurements that can indirectly probe new physics at scales beyond direct reach, plus a later energy leap that could open sensitivity to new heavy states, rare processes, and dark matter-related signatures. But so are the real-world constraints, multi-decade timelines, major R&D demands, especially high-field magnets and efficiency, and active debate around cost, energy use, and environmental footprint, which CERN and stakeholders are factoring into the feasibility and strategy discussions.